Hello everyone, we're excited to present neural microfacet fields, a new method for inverse rendering. Our method takes as input 100 images of a scene and recovers its geometry, materials, and illumination. The key to our method is a combination of the volume rendering and surface rendering paradigms. We model geometry using a density field as done by prior work for novel view synthesis, and we use a physically based shading model at each point in space with traditional Monte Carlo rendering. Starting from a pixel on the camera, we cast a ray through the volume and sample points along it. At each point, we query the scene for the volume density, which is used to accumulate the color from each sample along the ray according to the volume rendering formula. Each sample can also be treated as a surface oriented towards the negative gradient of the volume density, which we treat as a normal vector. The sample color is determined by the way the material at that point interacts with the incident light. This interaction can be represented using a bidirectional reflectance distribution function, or BRDF, which is often characterized by a lobe maximized around the reflected view direction. In order to compute the outgoing radiance, we integrate this function multiplied by the incoming light using Monte Carlo sampling, focusing most of our rays where the BRDF is maximized. We optimize density, materials, and environment by minimizing the L2 difference between rendered pixel values and the ground truth ones. Here, we show renderings of our model during the optimization on the toaster and car scenes. The ability of our model to represent a scene as a partially opaque field of particles is useful for optimization, but over time, our model converges into a well-defined and fully opaque surface. Our approach outperforms prior methods for inverse rendering, and its accurate decomposition of appearance into materials and illumination allows us to render the object in any environment. Here, we train the car scene, then render the car while rotating its recovered environment map, causing specular reflections on the car to move realistically across its surface. Although our method is designed for inverse rendering, and despite being designed for that task, it also obtains similar performance to state-of-the-art methods for novel view synthesis. We are also able to replace the lighting of more complex materials. Here, we train the materials scene and render it using the environment map recovered from the helmet scene. We can also use our scene decomposition to render new scenes by compositing objects into the same illumination. Here, we render our reconstructed car and toaster scenes together, including realistic interreflections between the two objects. Please see the paper for more details, and thanks for watching.